This video is continuing section 2.5 on the intersection of lines and planes. We're going to start section 2.5.3, the line of intersection of two planes. And in particular, we're going to do example 2.5.3. We're going to start that in this video, and in the next video, we are going to finish it. And the reason that we're splitting this example in two is because there are going to be two methods that we will see. In this video, we'll do method 1, the vector geometry approach to finding the line of intersection of two planes, and in the next video, we'll do method 2, a more algebraic approach that will be able to be extended in your next chapter about linear systems, where you'll be able to extend the algebraic method that we use to sort of bigger, more complicated situations. So let's go ahead and read example 2.5.3. So we're given two planes here, and we're asked first of all to use vector methods to show that the planes intersect at a line. And once we've done that, then we'll use method 1 to find that line of intersection. So the first thing that we need to do is just remember from our relative positions unit that two planes are intersecting at a line as long as their normal vectors are not parallel, which means that their normal vectors are not multiples of each other. So we can go and read the normal vectors here, and 1 from the first plane is 1, 1, minus 1, and 2 is 1, 1, 1. And I want to show that n1 is not k times n2. So let's create a little system of equations. n1, 1, 1, minus 1. If it were supposed to be k times n2, then it would be k, k, and k, and obviously k cannot be both minus 1 and 1 at the same time, so we have an inconsistency. And if that little system is inconsistent, then the normal vectors are not parallel, and therefore that was all we needed to show that the planes intersect at a line. So that's the first part done. And now we're going to go and use our method above to find the line of intersection using this method here, method 1. And as I said, in the next video, we'll do method 2. So method 1 here says the first thing we're going to do is find a direction vector on L and then find a point on L, because that's all we need to give the equation of a line, a point on the line, and a vector parallel to the line. So to find the direction vector of L, we're going to use some geometry here. We know that the line, if it's the line of intersection, that it's in both planes. And if it's in both planes, its direction vector has to be perpendicular to both normal vectors. And the cross product is a wonderful tool to give us vectors that are perpendicular to two other vectors at the same time. So we are going to take our direction vector as the cross product of the two normal vectors. So let's go and start with that. So we're going to let our direction vector D be n1 crossed with n2. So let's write those down, n1 and n2. Take the cross product, so 1 minus minus, so 1 plus 1 is 2, minus 1 minus 1, so minus 2, and 1 minus 1 gives me 0. So that's it for the direction vector. Now that's not all that I need. Obviously, to give a line, we've done this many times, we need to have a point on the line. And so we're going to use this logic. And that any line in three-dimensional space has to intersect at least one of the coordinate planes. It has to. And so we can choose to either let x equals 0, y equals 0, or z equals 0 to do this, do some high school algebra, I'll show you in just a second, to figure out a point on that line. So I'm going to choose to let x equal 0. And I will show you afterwards that one of them, z equals 0, actually wouldn't have worked. There will always be one of these that works. So if you find one that doesn't, we'll just try one of the others. And I'll show you afterwards why z equals 0 would not work. But if I let x equals 0 in the equations of the two planes, I'm getting this. So I'm getting y minus z is equal to 2, and I'm getting y plus z is equal to 1. A little system that from high school you can solve with any method that you want. I'm going to add the two equations together so that I get 2y is equal to 3 and y is 3 halves. And then substituting that back in, I see that z has to be equal to minus 1 half. So since x was 0, then what we have is a point 0, 3 halves, minus 1 half. And so since I have a point on the line and a vector parallel to the line, I can give the equation of the line of intersection x, y, z is the position vector of the point that we just found, 0, 3 halves, minus 1 half, plus t times the direction vector 2, minus 2, 0 for any t in R. So there is the answer. Now I'm going to go and show you what would have happened if you had chosen z equals 0, right? We did this one. There'll always be one that worked, but what does it look like if it doesn't work? I'm going to repeat this step here with z equals 0. So instead of let x equal 0, what if I had done this? If I had let z equal 0, and I'd gone into these equations here again. So if I'd had z equals 0, I would have had x plus y is equal to 2, and x plus y is equal to 1. Well, that can't be, right? What if I didn't notice and I subtracted? Well, then I'd get 0 is equal to 1, which should have be even more obvious that that doesn't work. That is inconsistent. And so what does that tell me geometrically? Well, z equals 0. Z equals 0 is the equation of the x, y plane. And so that tells me that my line doesn't intersect the xy plane. My line is parallel to the xy plane, right? So if this is our axes, x, y, and z, then the xy plane is, right, sitting sort of down here, flat, containing the x-axis and the y-axis. So our line is floating somewhere in space, somewhere above the xy plane, and just doesn't intersect, right? But it does intersect the other two coordinate planes. So if you get one that does not work, if you get sort of an inconsistency, that doesn't mean that there's no solution. That means you need to try one of the other planes, x equals 0, y equals 0, or z equals 0, whichever one you did not try. In the next video, we will go and see method 2 with the exact same example. So we'll finish example 2.5.3. We'll do method 2 in the next video to show an algebraic approach to this same problem.